We share
theoretical and empirical reviews.
It is all about learning research facts and sharing with others.
Title of the paper: Two-layer flows of generalized immiscible second-grade fluids in a rectangular channel. Authors of the paper: Details of the paper. Before we present the theoretical review, let us consider a preliminary introduction.
Some flows in the industry comprise more than a phase in local thermodynamic equilibrium, but such different phases are not necessarily in equilibrium with each other.
Examples of multi-phase flows mentioned by a scholar are gas-liquid flow in evaporators and condensers, gas-liquid-solid flows in chemical reactors, and solid gas flow as applicable in pneumatic.
Types of multi-phase flow are two-phase flow, gas-liquid flow, gas-solid flow, liquid-liquid flow, and liquid-solid flow, and three-phase flow, gas-liquid-solid flows, gas-liquid-liquid flows, and solid-liquid-liquid flows.
In the case of two-phase flows, chemical changes exist between the two phases. Also, special surface reactions at the phase interfaces, thermal differences due to different temperatures, phase inversion, and dynamic differences between phases are some of the conditions associated with the multi-phase flow, which is intrinsically a non-equilibrium process in nature, as pointed out by Oron and Boris, 2002.
In a study to explain flow patterns of oil-air-water, a three-phase flow through helically coiled tubes, some scholars remarked that the liquid-liquid, two-phase, flow pattern depends not only on the working fluid properties, flow conditions, and flow channel geometry, but also on the characteristics of the phase inversion, which is a unique phenomenon occurring in the liquid-liquid flow systems.
Also stated clearly that in the range of the low ratio of oil to water, the flow patterns of air-oil-water in horizontal straight tubes can be regarded as an extension of gas-liquid two-phase flow, but they are very different in helically coiled tubes.
Two-phase flow is encountered in the petroleum and nuclear industries. This led some scholars to explain the characteristics of gas-liquid flow at high pressures. It was concluded that vertical two-phase flow systems consist of a Taylor bubble, which is absent in steam-water flows at high pressures in a large diameter tube.
There are many kinds of non-Newtonian fluids. Some scholars describe the second-grade fluid as a subclass of non-Newtonian fluid in which velocity field has up to two derivatives in a stress-strain tensor relationship, whereas in the Newtonian fluid it has derivatives up to first order.
Navier-Stokes equation is most suitable to describe the dynamics of Newtonian fluids like water, because all the fluids in this category have a linear relationship between the shear stress and the shear strain. Non-Newtonian fluids are mainly classified into three categories based on their behavior in shear, as itemized by some scholars in the year 2010 are: 1. The shear stress of the fluids depends only on the rate of shear. 2. A fluid with a relationship between the shear stress and shear rate. 3. The fluids possess both elastic and viscous properties.
The second-grade fluid is one of the most popular models for non-Newtonian fluids. Some scholars used the second-order Rivlin-Eriksson model to simulate non-Newtonian second-grade fluid. Next, we shall now present the theoretical review.
The one-dimensional flow of two different second-grade fluids but immiscible through a rectangular channel due to the constant pressure gradient in the x direction was examined by the scholars.
The first second grade of the multi-phase flow occupies the lower domain, while the domain of the second grade is at the top.
Meanwhile, at y equals 0 and y equals d, the channel walls experience oscillating translational motions. The case of Caputo time fractional derivative, in which the history of the shear stress influences the velocity gradient, was sought for. Next is to present the empirical review.
After using the Laplace transform, the velocity gradient is in form of the convolution dependent on a kernel.
Meanwhile, parameter A1 is associated with the generalized fractional constitutive for the first second-grade fluid at the lower domain, and B1 for the second grade fluid at the upper domain. The analysis of the study shows that
the relationship between the kernel and a 1 is parabolic at the initial time, very small, but linear at a larger time. Based on this, it is worth remarking that time is a significant factor needed to understand the aforementioned transport phenomenon multiphase flow.
when t equals 0.05, increasing A1 and B1 cause the velocity and shear stress to rise. Although, the shear stress is smaller in the lower domain but higher in the upper domain. For A1 and B1 is within the range of 0 and 1, at the initial time, the shear rate and shear stress were controlled to accurately depict fractional derivatives of all orders less than 1.
But when the time was increased by 900%, increasing A1 and B1 caused the velocity and shear stress in both domains to decline as expected of second-grade fluids, as in the case of Caputo time fractional derivative. Acknowledgements. Special thanks to all the editors and reviewers of Mathematical Methods in the Applied Sciences, John Wiley and Sons, Limited. We share appreciates the contribution of the authors to the body of knowledge.